Hello everyone. In this video, we are going to talk about capacitances. So we can start by talking about a parallel plate capacitor, and we will kind of go back to our electric fields class where we talked about the setup with a couple of infinite parallel plates separated by some distance, and we'll call this distance d over here, right? And let's say that we have charged this setup such that there is plus charge on one of the plates. The first plate over here to the left has plus charge, and the second plate to the right has minus or negative charge. And let's say that we have charged it such that they both have the same surface charge density, in this case plus sigma over here and negative sigma over on the other side. So then from this setup, we know that the electric field in the middle, in between the two plates, that electric field here must be, and let me call this direction the x direction. So E vector has to be equal to sigma divided by epsilon 0 x hat, right? That's the electric field in the middle. And now this electric field, if these plates are really infinite, then this electric field has to be a uniform electric field that exists everywhere in between these two plates. And in fact, outside, on the left hand side of this plus plate, the electric field is 0. On the right hand side, the electric field is again 0. And in the middle, the electric field is that sigma over epsilon 0 x hat, and it's a uniform electric field. So now if I have electric field that is uniform, that looks like this, right? If this is the uniform electric field, you know that equipotential lines look exactly like this. They're perpendicular, right? They're perpendicular to the electric field line. So these lines are equipotential lines, right? So if those are equipotential lines, then from this picture, you can tell that the potential at the two surfaces to the plates, those have to be also equipotential lines, or in fact, equipotential surfaces, right? So since these are equipotential surfaces, they have constant potential, but one of the potentials, actually the plus charge is at a higher potential compared to the lower, to the minus charge. So this is at a higher potential, right? And that's at a lower potential. So can we find the potential difference? And in fact, that's not very difficult. The potential difference V, if let's say V is the potential difference between those 2 points, let's call it A and B. So V is equal to really VA minus VB, right? That is that potential difference. We'll call that the potential difference. So if that's the potential difference, we know that potential difference appears from if you remember, potential is equal to negative integral E dot dr. And in this case, we just have a constant electric field, so we can pull that out. So if I pull that out, the higher potential side is this, the lower potential side is that. So this should look like the electric field that is over here multiplied by the distance between the two plates. So we have sigma over epsilon 0 multiplied by d. Okay, so V is equal to sigma over epsilon 0 times d. All right, but what is sigma? Sigma is the charge density. So that's really the charge divided by the area of the plate, right? If the plate has some area A. Now, in reality, this is a practical plate, so it's not an infinite plate, right? So it has a finite area. It's just the idea that the area is much, much larger compared to anything comparable relative to the measurement of the separation between the two plates, that d, right? So d is a small quantity when you compare to the dimensions of the plates. That's the idea. And so we can think of practically these plates being infinitely large because the separation between them is sort of teensy. So with that idea, if I take sigma and plug in Q over A, then I get or Q times D divided by epsilon 0 times A. right? So I just substituted sigma is Q over A. Okay, so this means that V and Q are related. So V is equal to Q times D over epsilon 0 A. Okay, or I could rewrite this as Q is equal to V times epsilon 0 A over D. So this tells us that if I charge this setup which has a set of parallel plates, if I charge this by putting a battery in the circuit. So for instance, if I just take a battery and connect it across over here, right? So this is my battery with potential difference V. So it's gonna basically pump negative charges to this direction, or it's basically gonna send a negative charge, the electrons to this direction, pull in electrons from that direction, and it's gonna create this potential difference. And how is it going to create the potential difference across these 2 points of the capacitor? It's going to do that by depositing a certain amount of charge, a certain amount of positive charge to the positive plate and negative charge to the same amount of negative charge to the negative plate. Okay, so this equation is now telling us that if I put in a battery in the circuit, then how much charge can this setup hold? And the amount of charge, if this voltage was 1, then the amount of charge this can hold looks like Q equals epsilon 0 A over D, and that is referred to as the capacitance. How much charge can a circuit component hold if its potential difference has to be raised by 1 unit? Okay, so capacitance is really the measure of how much charge a circuit component can hold, and it is the amount of charge that you have to deposit into a circuit component to increase its potential difference across its ends by 1 unit. So in this particular example, we can then say Q equals V times C, where C, and now you see that the C only depends, it does not depend on Q or V, only depends on epsilon 0 A over D, which are properties of this parallel plate setup. A is the area of the of the plates, D is the separation between the two plates, and epsilon 0 is just a universal constant. So Q equals V times C. That's our main formula for capacitance. So a capacitance of 1, so the unit for capacitance, let's talk about that. So capacitance has units of farads, farad. 1 farad is 1 coulomb divided by 1 volt, right? So C is equal to Q over V. And again, in SI units, this becomes quite simple. So 1 coulomb divided by 1 volt is 1 farad. Okay? Great. So 1 coulomb is the amount of charge that you need to deposit on a capacitor with capacitance 1 farad to change the potential difference across its ends by that amount, 1 volt. All right, that's the idea. Now, this formula, although C equals epsilon 0 A over D, works only for parallel plate capacitors, right? This is for parallel plate capacitors. Okay, but this is generally true. Q equals C times V, or Q equals V times C. This is generally true for any capacitor. Okay, so now let's talk about a capacitor in a circuit. So how can I have a capacitor in a circuit? Well, the general symbol is just this parallel, two parallel plates. That's the symbol for a capacitor. Let's put the capacitor in a circuit with a battery and a resistor also in the same circuit. And let's call this battery the potential difference between the ends of the battery V, the capacitor is C, and the resistor, that's I. Okay, so now let's try to write the rules for this circuit, for writing sort of determining how much charge gets deposited on the capacitor, how much current flows through resistor, etc., etc. In order to do that, we got to remember that when the capacitor is charging, so at the very beginning, let's say I have a switch over here that I just connect to close the circuit, then charge is going to start flowing from the positive end of the battery. And it's going to start accumulating on this positive plate of the capacitor. And how's that going to work? Well, if the battery is sending some current out, it's also getting some current in. So that's going to make a negative charge on the other side of the other plate of the capacitor, right? That's how it's going to work. All right. So what is happening is that there's going to be charge flowing through the circuit. So remember, flow of charge is current, and how is charge and current related? Well, I is equal to dq dt. So if the capacitor gains a charge q, right, at any point of time, if q of t is the charge on the positive plate of the capacitor, then dq dt is the current that is flowing in this direction in the circuit. Okay, but now we can write the potential drop across the capacitor using our previous formula. So remember, Q is equal to V times C. So the VC, the drop across the capacitor going from this end to that end. Okay, remember, this is the positive plate of the capacitor, that's the negative plate, so that's a decrease in potential. Okay, so that potential drop across the capacitor is just QT over C. And all I did was just took this formula, Q equals CV, and just replace and find V, right? So this is a drop. So since this is a drop, when I use in Kirchhoff's loop rule, I'd have to treat this as a drop. So this is going to be negative QT over C when I write it in Kirchhoff's rule. So similarly, what is the drop across a resistor? We know that is by Ohm's law, that is VR is equal to I times R. And then as I go around through the battery, the potential actually increases. So let's write Kirchhoff's loop rule. So if I want to write Kirchhoff's loop rule, then that will look like starting from this point, the point over here, I go through the capacitor, so the potential drops. So we get a negative VC. Then through the resistor, again the potential drops, negative VR, and then the potential increases, plus V is equal to 0. And so let's plug that in. We now have negative QT over C minus I times R plus V equals 0. But what is I? Well, remember this is going to be a function of time, because now as the capacitor gets more and more charged, the rate of flow of that charge is going to change. And rate of flow of that charge is really current. So I is a function of time, and it's equal to dq dt. Okay? So let's plug that in. So what we have now looks like V, so I'm going to rewrite this equation over here. V is equal to IR, but I is dq dt. So dq dt times R, okay, plus Q over C. All right, and we can go one step further and write this as V divided by R is equal to dq dt plus Q over CR. Now this is a differential equation that we can solve. We'll sort of try to solve this in a very simple way, okay, without getting into differential equations. There's sort of a very easy way of solving that. So what we will do is we will rewrite this as dq dt is equal to V over R minus Q over CR. Okay, and then we can then rewrite this as dq divided by V over R minus Q over CR is equal to dt. All right, so I brought everything that was over here on the right hand side to the denominator of the left hand side and took the dt to the other side, and now we can integrate it from time t equals 0 to some time t. At the initial instant, if you think about it, because we are charging the capacitor, at the initial instant, the charge on the capacitor must have been 0. So we'll start the integral from 0 and go to qt. And for the sake of completeness, we should probably put primes on these variables there. So our next step is to do this integral. So we are going to sort of rewrite this integral in a slightly different way. So what we're going to do is we're going to make this denominator look a little more tractable. So we'll have dq prime, and then we will write here, we'll take the CR sort of as a common denominator of that denominator and put it in the numerator. So we'll have CR times over here CV minus Q prime, and the limits are still 0 to Qt is equal to integral of 0 to of dt prime from 0 to t. That just gives us t, right? So we can just do that integral. So this will give us, on the left hand side, when we do this integral, that's a simple one. That's just a log. So we will get log of CV divided by CV minus Q of t. And then we can divide both sides by that CR. So we'll have, on the right hand side, we'll have t over CR, right? So this will give us then, now we can exponentiate both sides. So that will give us CV over CV minus Q of t is equal to e to the t over CR. And we can sort of simplify this even further and write CV times e to the negative t over CR is equal to CV minus QT. And now if we rearrange this equation, then we get Q of t is equal to C times V. And then so we're bringing Q of t to this side and CV times e to the negative t over CR to the other side. So we have CV times 1 minus e to the negative t over CR. Okay, so this is what the charge as a function of time on a capacitor looks like in a charging circuit. And so what does that mean? Well, a few things to notice is that if I put in t equals 0, then Q at t equals 0, right? So if I put in t equals 0, this term becomes a 1. 1 minus 1 is a 0, so that gives a 0. And what happens if I put t equals infinity? So t equals infinity means the second term becomes 0 because exponential negative infinity over any number, that's a 0. So Q at t equals infinity is C times V. Okay, so but what is this? This is, if you look at it, remember Q equals CV is the net charge the capacitor gains, which means that after infinite time, the capacitor is now fully charged, right? So that's why Q is equal to C times V in that scenario. Okay, now what about the current? So because we know the charge, we can also find the current. So I as a function of t is equal to dq dt, and I can just take derivatives now. So the first term, its derivative is going to be 0 because it's a constant. But the second term's derivative will give us negative CV times negative 1 over CR times e to the negative t over CR. Okay, and here the negatives will cancel and the c will cancel. So this will give us IT is equal to V over R times e to the negative t over CR. So that's the current through a capacitor. And this tells us, again, at t equals 0, I at t equals 0 is equal to V over R. And at t equals infinity, I at t equals infinity, that is equal to, as t goes to infinity, this becomes 0. So after infinite time, the capacitive circuit has no current anymore. Now that we know how to charge a capacitor, let's think about what happens when we discharge a capacitor. So again, we'll have a similar circuit, except this time in the circuit, we will have a fully charged capacitor with charge Q. And now we have a switch. So at time t equals 0, we will close the switch and the circuit has a resistor in it. Okay, so what happens is now we can again do the Kirchhoff rule for this loop. And as you can see, so if this is the positive charge, that's the negative charge. Now there's an excess of positive charge on one side and an excess of negative side on charge on the other side. So the charge is going to now start flowing from the positive end to the negative end like that. So there's going to be a current I. And here it's crucial to note that this I is really the rate at which the charge on the positive plate is decreasing, which means I is equal to negative dq dt. Okay, negative because the charge is decreasing. Okay, so now as we go along this circuit, then we can again do Kirchhoff's voltage rule. And so in order to do that, remember the voltage drop across the capacitor from the positive to the negative end, that was V equals Q over C. So Q is a function of T over C. That's the Kirchhoff's, that's sort of the voltage drop. And so as we're applying the Kirchhoff rule, we went from here to here. So that was the QT over C drop. That's a negative drop because it goes from the positive to the negative side. And now as we go through the resistor, we are going against the current. So that's a plus I times R, and that net thing is equal to 0. So which tells us IR is equal to QT over C. But IR's I is equal to negative dq dt. So if that we plug that in, we get dq dt is equal to negative q as a function of time over c times r. This is a much simpler differential equation to solve, and we can in fact write dq divided by q is equal to negative dt over cr, and quite easily integrate both sides from t equals 0 to t, and this side we will integrate from q0 to q as a function of time. And so we should change all these labels. And so we will get, on the first side, we will get natural log of q as a function of t divided by q0 is equal to negative t over cr. And so this will imply q as a function of time is equal to q0 times e to the negative t over cr. So this is what happens when a capacitor gets discharged, right? So as it's getting discharged, you can see then t equals 0. At t equals 0, q at t equals 0, that's just the initial charge on the capacitor, which is q0. At t equals infinity, q as t goes to infinity becomes 0, right? So it takes an infinite amount of time to get the charge on a capacitor to go to 0. But of course, there is a practical limitation on how much charge is actually detectable, or how much charge even makes sense to have on a capacitor. And usually what we say is that once, because this is an exponential decay, once the charge on the capacitor has gone down to about 1 over e of the initial charge, so that would happen when t is equal to CR. Okay, so when t equals CR, then q at t equals CR, that is equal to q0 over e. So the charge has gone down to the initial charge divided by an amount e. So at that point, we will say that the capacitor is sort of discharged. And so this is often referred to as the time constant of a capacitive circuit. Let's briefly talk about the units over here. So as you see, the time constant we often refer to as tau. Tau equals c times r. Time constant, this is a time, so this better have units of second. So 1 second. And so this must be equal to, on the other side, the unit of capacitance is farad. So 1 farad multiplied by the unit of resistance is ohm. So 1 second equals 1 farad times 1 ohm. Let's now talk about circuits in which there are more than one capacitances and how we can combine capacitors. So let's think about a circuit where I have two capacitors in series in this fashion. And let's say that I have put them across a battery. There is no resistor in the circuit. We'll just try to figure out how capacitances work. Okay, so what will happen when I put a circuit like this plus charge battery, the plus side of the battery is going to start pumping in charge. So this part is going to get positively charged. And the negative side of the battery is going to pull in some charge. So this side is going to get negatively charged. Okay, but now the middle portion over here, if you notice that, that is not connected to anything else. So this positive charge better induce a negative charge on this side and a positive charge on that side. And so this is the general rule, right? So if you see any combination that looks like this, the negative and the positive charges better sort of orient themselves such that the one that is closer to the plate that has a positive charge becomes a negative charge, and the other side becomes a positive charge, which then again is closer to the another plate that has a negative charge. Okay, so now if you think about the amount of charges that these plates are going to have, if the first plate has a charge Q, the second plate better also have the same charge but negative Q. And of course, in order for this to make sense, this other side has to have positive Q and this one has to have negative Q. Okay, all right. So this is our combination. And now let's call these two capacitances C1 and C2. Okay, so the equivalent capacitance of this circuit then looks like this, with again the same charge, Q and negative Q plus Q and negative Q, but now the capacitance is C equivalent. Okay, so how do we make sense of this? Well, the potential drop across the first capacitance, let's call that V1, and across the second capacitance, let's call that V2, and the equivalent of this drop V1 plus V2, right? So going across the circuit, right? V1 plus V2, that is equal to V, right? That is the actual drop across the battery. All right, great. So if that's true, can we now represent each of these V's in terms of the capacitances themselves? Remember the capacitance formula Q equals CV, or V1 is equal to Q over C1, and the second one is plus Q over C2. But notice that from this other picture, we have this equal to Q over C equivalent. All right, so now the Q's can be canceled, so we figure out that 1 over C equivalent is equal to 1 over C1 plus 1 over C2. And in fact, this formula can be continued with situations where you have 2, 3, 4, or more capacitances, C1, C2, C3, C4, etc. in series. So this is a circuit where the capacitances are in series. So for the series situation, 1 over C equivalent looks like that is equal to sum over I equals 1 through n, 1 over Ci for n capacitors in series. Okay, so that is the formula. And in fact, for the two situation, this looks like C equivalent is equal to C1, C2 divided by C1 plus C2. And if you notice, this factor, the C1, C2 over C1 plus C2 is actually less than, so C equivalent in this case is actually less than C1 and C2 individually, right? Because if I think about C2 as the factor that I'm looking at, then C1 times C1 plus C2, this factor is less than 1. So C equivalent must be less than C2. But similarly, when I take C1, C2 divided by C1 plus C2 is also less than 1, which means C equivalent is less than C1. So you can independently see that C equivalent is less than C1 and C2, which means that if you put two capacitors in series, then the equivalent capacitance is lower than the least of the two capacitances. And this will be true in the case when you have a series combination of more than two capacitances as well. The equivalent capacitance is going to be less than the lowest of those capacitances. Let's now briefly talk about what happens if we have capacitors in parallel. And so capacitance is in parallel like this. So here, of course, um, when the charge goes through, the charge that is deposited on the first and the second don't necessarily have to be the same. They will be different from each other, plus here and minus on this side. And this can then be put together in an equivalent picture which would look like this, where the net charge is Q, okay, plus on this side, negative on this side. But this would mean that Q is equal to Q1 plus Q2. And we can again play the same game by writing Q is equal to C times V, in this case C equivalent times V. But so C equivalent times V is equal to C1 times V, because the potential difference across both the capacitors is exactly the same, C1 times V plus C2 times V. And as usual, we can cancel off V from both sides, and so we get C equivalent equals C1 plus C2. So this is what happens when we have two capacitors in parallel. Okay, now if I had more than two capacitors in parallel, if I had a circuit which had 2, 3, 4, or even more capacitors in parallel to a battery, so C1, C2, C3, C4 if you like, and goes on, then C equivalent for that parallel circuit is I equals 1 through n C I, where n is the number of capacitors in parallel. Okay. Okay, so that's the idea. When you combine capacitors in parallel, you add their capacitances together. Needless to say that the sum total of all these capacitances is going to be larger than the largest of the capacitances in the circuit.